All right, here's problem number 18. For problem number 18, one of the key things to recognize. All right, so let me read it first, and then we'll go into the key thing to recognize. It says Kepler 1656b is an exoplanet orbiting a star about one solar mass. A. What is the orbital period in days, round to two places past the decimal? The semi-major axis of its orbit is 0.2 astronomical units. Part B, calculate the maximum Doppler shift that could be observed with this planet. All right, and we're going to round to two places. So we're going to do really part A needs to be in scientific notation. You'll see what I mean. Actually, I don't think, now that I think about it, I don't know that either of them need to be in scientific notation. We'll see that in just a second. I think I might have not had, I shouldn't have included that. Anyhow, we're going to round it to two places past the decimal. All right, so we'll see. All right, so if we look at this, the key thing to recognize is this part right here, that it's a one solar mass star. So you have a planet orbiting a star that is the same mass as the sun, that's what one solar mass means, of course. And that means that we can use Kepler's third law, a cubed equals p squared. All right, where a is the semi-major axis and p is the period in years. All right, so the first part A, says what's the orbital period. All right, so part A is just solving this for p, right? The period is, of course, going to be the square root of a cubed. All right, now the period comes out in years, so we do have to convert it to days, but that's going to be pretty trivial. So it's going to be equal to the square root of 0.2 astronomical units. Remember, A has to be in astronomical units, and it's given to us right here, 0.2 AU, and I've got to cube that. All right, so I'm going to get my calculator, and well, I guess I could use the computer calculator right here. All right, there we go. All right, and so we have 0.2. Let's see if I remember how to do this one. Raised to the third power equals. All right, and then we take the square root of that. All right, and there it is. Okay, so that's the period in years. So it's 0.089. So here, I'll just write this part. So this is not the final answer. It's 0.089 years. All right, so I'm going to use the unrounded version of this and then convert it. Of course, look, so we know that what do we have to convert this to? Days, right? It says it right there, days. All right, so we're going to use that 1 year is 365.2422 days. All right, so you just take this number, and that's on the formula sheet, of course. So take this number, and we're going to multiply it times 365.24. Right? It's actually technically 2422 days. All right, so that's exactly the number of days in a year, and so it takes this exoplanet, which is they designate it by this was the satellite that found it, the Kepler satellite. This was that's just the designation of it. Anyhow, the period here turns out to be, I want to write it here. So what was it? 32. Here, let's see. We're going to round it to, it says two places past the decimal. Here, I forgot what it was already. So 32.67 days. 0.67 days. All right. So now we really need to keep going with that. because so to figure out the Doppler shift. So this is part B I'm working on now. For part B, we need to know the velocity of this thing in the velocity of the exoplanet in kilometers per second. Right. That's not how you figure to get the Doppler shift. It's going to be the velocity divided by the speed of light in kilometers per second. So whatever our velocity is, we're this is going to equal 3 times 10 to the fifth kilometers per second, right? That because that's the speed of light in kilometers per second, right? So we got to work on this part, right? That figuring out what is the velocity of this planet as it goes around its star, right? So it's going in a circle as usual. This is the radius right here. Now they give us the radius in. Well, actually, before I do that, let me just put this. The radius is 0.2 AU, and then of course we. 0.2. 0.2, I didn't mean to put the decimal that far away from the 2. 0.2 AU. And then in 1 AU, there are, so in kilometers, it's 150 million. So 150 times 10 to the 6th kilometers. All right, that's what 1 AU is. So 0.2 times that. All right, so here, I'm going to do it in my scientific calculator because it just does a much better job. All right, so it's going to be 0.2 times 150 times 10 to the 6th. All right, so 0.2 times that, it turns out to be, all right, so it's going to be 3 times 10 to the, let's see, 1, 2, 3. Times 10 to the 7th. All right, so this is what R is. All right, R is 3 times 10 to the 7th kilometers. All right, now to get the velocity, remember it's going around in a circle, and the circumference of any circle is always 2 pi. So it's 2 pi times the radius. All right, so the velocity here. The velocity is going to be 2 pi times this number that's in your calculator, which is 3 times 10 to the 7th. All right, and of course that's got to be in kilometers. Right now, we still have to divide by the period in seconds. All right, now we have the period up here in days, so we're gonna convert it to seconds in seconds. Right, and seconds. Right. So wait, let me do this part, the numerator first. Right, so times 2 pi. All right, so this is let's see, 1, 2, 3. 1, 2, 3. So I get something like 1.88 times 10 to the 8th. Let me just check on that real quick. Times 10 to the 8th. Yeah. Okay. So this becomes so the numerator of this is 1.88 times 10 to the 8th kilometers. Remember, we got to get it in kilometers per second. All right, so times. All right, so we got that. Let me store that in my calculator. Right, so I got that. And then what I'm going to do is I'm going to turn this 32.6 days. That's point. That doesn't look like a decimal, does it? 32.6 days. Okay. So actually, I'm going to do the unrounded version of it. All right, so let's see, it's the square root of 0.2 raised to the third. I'm just redoing the calculation. All right, and then times 365.2422 equals. All right, so that's the 32.668 some days, and then times 24, and then times 60, and then times 60 again. All right, because of course there's 60 minutes. There's 60 minutes in an hour, 60 seconds in a minute. All right. Anyhow, so that gives me the period. So I'm going to put this in the denominator. So this is, what is this? 1, 2, 3. So it would be 2.8. So this is the denominator in seconds. 2.8225. 37.275 or something. It doesn't really matter here. 275. All right, so you got that, and we're gonna take the number that we have in the numerator, the 1.88 times 10 to the 8th, and divide it by that number. Okay, so let me do this correctly. Divided by that equals. All right. So the velocity, as this thing is going around its star, turns out to be about 66.78 kilometers per second. All right. And so the kilometers per second go away. That's gone. All right. So you're just taking the 66.78 roughly, or just you take the unrounded version of that, and then you divide it by the speed of light in kilometers per second. So divided by 3 times 10 to the 5th. All right. And so this is what's called the Doppler shift. This V over C. All right. The velocity divided by the speed of light. And so you want them to be in the same units. All right. So because of course the kilometers per second have to cancel. So this turns out to be, and this is what's called the Doppler shift. It turns out to be it's a very small number, 2.2. It's like 2.226, or I'm going to say 2.23 times 10 to the minus 4th. Remember the way this is exactly how you'd enter it into Blackboard, right? 2.23 e minus 4, right? That's how Blackboard interprets times 10 to the minus 4th. All right, so that's literally part B. That's the Doppler shift. All right, for this particular planet. All right, so that is problem number 18.